Imagine an EV battery that lasts millions of miles and charges in minutes. Sounds like a sci-fi, but some labs and companies are close. But the catch is this: lab miracles don't always fit into cars overnight. This video walks the line between the hype and hard results. I'll show the biggest recent battery stories, a lab cell that survived 20,000 cycles, major advances in solid state and sodium ion works, and industrial moves to scale, and then I'll connect the dots so you know what will actually reach drivers first and what will stay an R&D headline for years. Every claim is tied to a real study or industry move, so you can tell data from this spin. The big recent wins. What the headlines mean. Researchers demonstrated a lithium cell using a single crystal electrode that ran over 20,000 cycles and still held about 80% capacity, a number people translate into the equivalent of millions of kilometers of driving. That's huge because the science shows the single crystal structure resists the tiny particle cracking that kills most cells over time. But before you revise your replacement plans, remember that number is for a controlled lab cell, not a full automotive pack. And real cars face fast charging, temperature swings, and mechanical stresses that shortens life. Dalhousie University led the work and used advanced synchrotron imaging to directly observe how the cell stayed intact. Fast charging and solid-state gains. Several companies and partnerships are reporting material progress in solid-state electrolytes and lithium metal anodes, technology that promises higher energy density and safer packs that can charge faster. Automotive groups and startups claim validated cells and pilot production plans, and a few industry partners are moving toward demonstrator fleets. But manufacturing solid electrolyte at scale, integrating lithium metal anodes safely, and keeping costs reasonable are massive engineering hurdles. So the timeline for mass rollout is measured in years, not months. Cheaper, safer alternatives. Sodium-ion batteries are making real commercial steps. They're cheaper, use abundant raw materials, and recent industrial announcements show mass production is possible. And vehicle launches planned. For mid-range use and cold climates, sodium ion is now viable in passenger cars and grid storage. But sodium ion still lags lithium ion in energy density for long-range EVs, so think of it as complementary. Great for lower cost, shorter range models and big stationary storage, not a universal replacement yet. Labs can tune every condition: charge, discharge profile, temperature, pressure, and cell format. That's how you get jaw-dropping cycle counts or charging rates in a paper. But the real world throws everything at a pack. DC fast charging, potholes, extreme heat, salty roads, and years of use. A car battery must survive all that while remaining safe and affordable. That's the engineering gulf to cross. Why scale and integration matter. A single high-performance cell is encouraging, but automotive packs contain hundreds or thousands of cells. BMS electronics and bus bars, cooling and structural supports. Scaling a lab recipe to thousands of cells means confronting yield, cost manufacturability, and safety certification. Big companies are doing that work now. But it takes time and investments. Car makers are publicly investing in next-generation technology and pilot production, and trade announcements show serious scale plans. If longevity is king, how single crystal helps? Single crystal cathodes reduce micro-crack formation. That translates to far fewer lost connections inside the particles and slower capacity fades. For fleets or rideshare cars that rack up miles quickly, this could mean batteries that remain useful for longer and higher second life value as grid storage. The study showing 20,000 cycles makes the economics attractive on paper. But to turn that into a cheaper EV, you must make the material at scale and prove pack reliability under fast charging and crash conditions. That requires a multi-year qualification cycle. If fast fill-ups are the prize, solid-state and new chemistries. Solid-state and lithium metal anodes promise both energy density and quick charge rates. Test and pilot cells suggest charging times dropping to minutes, and some partnerships aim for demonstrator vehicles within a few years. For long-distance travel, that's the most disruptive change. Quick fills that match the convenience of gasoline. But solid electrolytes and lithium metal introduce new failure modes, dendrite, interface breakdown, and need manufacturing tools. Expect initial deployment in premium segments or controlled fleets then wider rollout as production improves. If cost and supply chains rule sodium-ion and hybrid systems, companies like CATL and other manufacturers are moving sodium-ion from labs into production and vehicles. Sodium's big win is raw material availability and cost. That helps to scale EV adoption where cost is the biggest barrier. For urban commuters or entry EVs, sodium-ion gives comparable cold weather performance and acceptable range at lower cost. But for buyers who need 300 plus mile range and ultra lightweight packs now, sodium-ion is not the complete answer. It's a strong option in a mixed portfolio of battery types. What actually changes for drivers first? The short, practical list of likely near-term changes. First, longer-lasting cells in commercial cars. Incremental gains from improved electrode designs, like single crystal concepts, will appear first in premium and then mainstream models as suppliers scale. Expect noticeable warranty or degradation improvements within a few model years if scale economics holds. Second, fast charging improvements via hybrid approaches. Better thermal systems plus incremental cell improvements will make 15 to 30 minute, 10 to 80% sessions more common before true 5-minute charging is mainstream. Solid-state shortcuts may appear in demo fleets sooner than mass market. 3. Broader use of sodium-ion and dual battery options for cost-sensitive cars and storage systems. Manufacturers will mix chemistries to match price or performance needs. The but that keeps expectations honest. All these advances are real and backed by labs and pilot programs. But none are a switch you can flip globally tomorrow. Each requires supply chain scale, manufacturing reliability and safety validation, and cost reduction. That's why automakers and battery firms are running parallel paths. Scale better lithium variants now, pilot solid state where it makes sense, and deploy sodium-ion where cost matters. 3 simple takeaways for drivers and buyers. First, celebrate the wins. The 20,000 cycle single crystal result and the solid-state pilots are real science, not a vaporware. They point to batteries that last longer, charge faster, and cost less in the long run. Second, but expect timelines. Real, safe, affordable mass production takes years. Don't expect millions of cars with 5-minute charging or infinity life in the next model year. The next decade will be mixed. We'll see better lithium designs roll out into many cars. Sodium-ion in a budget and city models, and solid-state or lithium metal appear first in premium commercial vehicles. That mix is a realistic path to faster, cheaper, and more durable EVs. If you want to learn more about the battery management system inside the electric vehicles, how it calculates state of charge, state of health, and other characteristics, you can click on the link in the description. Thank you.